Nice to see you. So let us recall what we did before um, this weekend. So we introduced the solenoid. Who will tell me what is solenoid?
It's a conductor which is bent and spiral.
Okay, so it's a special configuration of electric current, which allows us what?
Enhance magnetic field
Where?
in the inner part of the spiral.
Like inside, yes, of the solenoid. So because of special configuration of electric current, magnetic field which creates from like originates from each of the coil, each turn of the solenoid will kind of add up, and that results in uniform and quite strong magnetic field in this internal volume of the solenoid. So what approach we applied in order to determine magnetic field uh, magnitude inside solenoid? Did you
Apply
Ampere's law? So what Ampere's law tells us? That the integral of
dot product of magnetic field vector and TS vector gives us product of current and mu naught.
mu naught, and this current is the current which flows through the area of the closed loop along which we did the integration. So by applying this Ampere's law to a solenoid structure, we took into account that the magnetic field inside solenoid is much stronger than outside, and that led us to the result, the equation which gives us the magnitude of magnetic field inside solenoid, that is V equals to mu naught times n, like small n, times I. And this small n, that is number of coils of solenoid per unit. So if we want to make strong magnetic field with limited magnitude of electric current, we want to increase this number of coils. So also we introduced last time the flux of magnetic field. So that is the integral of scalar product of magnetic field vector and area vector, dA vector. And in terms of magnitude, it's the magnitude of magnetic field vector times area times cosine theta, angle between the magnetic field vector and normal vector to the area which we are considering. So why that is important? Because today we continue this topic, magnetic field, but specifically how magnetic field changes over time and what it results. So there are two laws which we kind of will discuss today. So Faraday's law and Lenz's law, they are quite connected to each other. And that's all about induced electromotive force and induced electric current. So the thing is that so far we considered that the source of electric field as electric charge and source of magnetic field is mobile electric charges. However, there is a relationship between magnetic field and electric field, in particular of their changing over time. So it is possible, according to Lenz's law, according to Faraday's law, to create electromotive force in a conductor if we change the magnetic field flux over time through this conductor. There are different options. We will consider different options how we can change that magnetic field flux. But if magnetic field flux is changing, that results in electromotive induced so-called electromotive force. And if we have a closed electric circuit, obviously some electromotive force will result in some induced current which is floating through this circuit. So how does it work? Let me share with you the screen. So if, for instance, we have some, let's say we operate this multimeter as a voltmeter in the voltmeter regime. So we have some current loop, some wire, and we place a permanent magnet closer to this loop. So that will increase or decrease magnetic field flux. If we place this permanent magnet closer to the loop. So what magnetic field flux is? Magnitude of magnetic field times area times cosine angle. So here, let's say it's kind of perpendicular, so we don't think about angle. So we have magnetic field and area. Does area change? No, area doesn't change, but magnetic field does. So we place magnet closer, means we increase magnetic field in the area, in the vicinity of this loop, and that results in the increase of magnetic field flux through this loop. So that will result in certain induced electromotive force within this wire, which can be measured with the volt. If we switch, for instance, this multimeter from voltmeter to ampermeter mode, we will measure some induced current. This induced current, its direction, will be following, and actually the polarity of the induced electromotive force and direction of induced current, they will follow Lenz's law, which tells us that always induced electromotive force and induced current will oppose the reason which causes this generation, like induction of electromotive force and current. So, for instance, here, when we place this magnet closer to the loop, the magnetic field flux increases. So it changes in time, but it increases. So the induced current, which will flow in this circuit because of this, will create magnetic field in order to oppose the increase of the magnetic field flux originated from external magnetic field. So that's why we will mention it in the quantitative form later when we write the Faraday's law. We have this minus in front of the equation, which tells us that according to Lenz's law, this induced current always opposes the reason for inducing this current. And in this case, opposing the increase of magnetic field flux. So if we don't move the permanent magnet, nothing happens. This area is constant. Magnetic field next to the loop is also constant. So no changes happen. There is no change of magnetic field flux over time, and our instrument is showing zero, which is valid for both voltage, like electromotive force, and current. However, if we start to move this magnet away from the loop, we reduce magnetic field. In this case, the magnetic field flux is dropping, and that causes already both electromotive force and induced electromotive force and induced current. And you see that here we have different polarities. minus and plus, because in this case the magnetic field flux was increasing, in this case it's decreasing, and that's why the direction of induced electric current are also opposite. Before we proceed further, who remembers what is the difference between voltmeter and ampere meter? A key fundamental difference. Huh? That's correct in its way, because we connect it in different options, in different ways. However, let's say our circuit is just this loop. So there are two terminals. You cannot connect in different ways. So you will connect it always like this, no matter what you connect, ampere meter or voltmeter. So what is inside this device different and defines the possibility to measure current and voltage? It's resistance. Internal resistance, exactly. Because if we want to measure current, we don't want to interfere with the electric circuit, which we want to measure. So we want to connect in series, we need to connect in series. And in that case, the resistance, internal resistance of the device, in order to have minimum impact on the measured current, should be very small. In opposite, if we measure voltage, the connection is in parallel, and we want to make sure that there's minimum current flowing through the voltmeter in order to show the correct voltage drop over the part of the circuit. So that is important. So another option how we can show the induced electromotive force and induced current. So imagine we have some iron core which is electrically insulated, so it doesn't, and wires are also covered with insulation. So we have some primary and secondary coil, and here is battery. So we turn on this switcher. What happens here? We start to increase current, and a bit later we will consider RL electric circuits, resistor inductor. So because of some inductance of this coil, the current will not increase like instantaneously. It will increase according to some time dependence, but it will happen quite fast. So we will have quite fast increase in electric current here, and that electric current will create magnetic field flux through this iron core. So these two wires are decoupled electric. We do not have any electrical contacts between them. However, just because of variable in time magnetic field flux through this iron core, in the second coil, we will see some induced electromotive force, or if we measure current, induced current. If we switch it, so let's say it's on, it reaches some saturation, this current goes to maximum magnitude, which is defined by resistance of this coil and potential difference at the terminals of the battery. Then we have stationary condition, nothing is changing. Magnetic field flux remains constant, and in that case we will not measure anything, because no magnetic field flux change over time, no induced electromotive force. If we now switch off this electric circuit, current will decrease, and that will result in reduction. So initially we were increasing magnetic field flux. Now, since current is off, we will reduce magnetic field flux, and that will also induce electromotive force and induce current. However, in opposite direction, because now magnetic field flux is dropping. So there are different applications of Faraday's law and induced electromotive forces. So there are so-called protective electric circuit breakers. So instead, because there are different electric circuit breakers, one when you protect from short circuit, so you literally short circuit your power outlet, current increases beyond some threshold level, and circuit breaker opens the circuit so you don't burn the house. However, this type of devices, which are called differential circuit breakers, they are designed not to save the house, but actually save you. Because sometimes when you deal with, that happens in most cases when you deal with some devices which have electrical actuators, it's possible that insulation of the wire is damaged and potential from the phase of electric power outlet goes to the metal housing of your device. In that case, you will get, with respect to the ground where you stand, 200, if we are talking about our electric power grid, 220 volts with respect to the ground. If a person touches such housing, which is under potential because of damaged wire inside, then obviously there will be a huge potential difference. And depending on insulation, which is always not perfect, and climate conditions and health conditions of the person, there will be some current flowing through the human body. That can be deadly. And this device, what it does, yeah, you have a question? No, no question? Okay. So, what this device does? So, this is wire which goes into the, let's say, apartment or house. This is phase and this is zero. We have two wires. So current flows in, flows out. We have this iron core around these two wires. Imagine that everything is fine. We don't have any situation when there is potential on metal housing and everything operates under normal conditions. According to discontinuity of, continuity of electric charge and conservation of electric charge, we have equal currents which flows in and out. Means they compensate each other in terms of magnetic field which is created. And in this core, metal core, there is no change of magnetic field flux because these currents compensate each other's contribution to the magnetic field. However, if there is some emergency case and part of the electric current is flowing through the person to the ground, there will be small difference between these two currents. Small difference in these two currents will result in some resultant magnetic field which will not be compensated anymore because these currents will not be the same. Part will be going somewhere from the circuit to the ground within the building. And that will create some excessive magnetic field, will create induced electromotive force in this coil. Once this induced electromotive force is detected by the electric circuit of this differential circuit breaker, it will just open, like switch off the electric circuit, and there will be no current supplied to the house. So that's an option how you can protect human beings from being damaged by electrical current. So let us switch to equations a little bit. So Faraday's law tells us that induced electromotive force is equal to negative of first derivative of magnetic field flux over time. So this minus, which we have here, that is Lenz's law, which tells us the orientation of like polarity and direction of induced electromotive force and induced current, which always opposes the reason caused this currents and electromotive force. If we have not just one coil, some loop, let's say, of electric wire, but several, let's say we have a N, capital N loops, then we need to take that into account. So induced electromotive force will significantly increase depending how many turns of wires we are dealing with. So now if we consider some wireframe, let's say it will be positioned at some angle with respect to magnetic field vector. So this is magnetic field vector, and this is direction of the normal to the surface of this current loop. So here we have some angle theta. So the flux through such area of magnetic field will be given as follows if we operate with magnitudes of this magnitude of this flux. So it will be magnitude of magnetic field times magnitude of the area times cosine theta, angle between the normal to the area of this current of this wire loop and the magnetic field vector. So we remember this from our previous discussion, and in that case the electromotive force which can be induced in such current loop or like wire loop will be defined as negative first derivative over time of product b times a times cosine theta. And now let us discuss what can be the reason for magnetic field flux through these wire loops to change over time. So what can change here over time? Okay, so theta as a function of time. We can rotate this wire loop. We will change orientation with respect to fixed position, like orientation of magnetic field vector, and that will cause change of the magnetic field flux. What else? Yes, magnetic field also can be, and area. So these are the options when we may end up with the situation that magnetic field flux is changing over time, and that will result in induced electromotive force and current, according to Faraday's law. So now let us consider first option when we deal with magnetic field as a function of time. So that will be given with the following equation, will be B naught exponent minus A times T. So that's some exponential dependence for magnetic magnitude of magnetic field. So if we plot magnitude of magnetic field versus time, we will see some exponential decay. So it's quite fast decay of magnetic field magnitude. So in this case, electromotive force is equal to negative dFb over dt according to Faraday's law, and we take this derivative. So it's derivative over first derivative over time of this expression. So it will be area times b naught times exponent minus a times t. And we assume that this magnetic field vector goes perpendicularly to the surface of the loop, so we don't consider any angles between. So cosine theta should be equal to zero, to unity. So now area stays constant. B naught, this pre-exponential factor, is also constant. We need to factor them out from this derivative. So it will be a times b naught d over dt exponent minus a t. So what will be this derivative? Here will be minus a times exponent minus at. And eventually we cancel out these two minuses. We will get a small times area times b naught exponent minus at. So this is the expression for electromotive force. And we can write here that this induced electromotive force will also be a function of time.
But this A is in common.
It's just some coefficient in the argument next to the time. It just defines the time dependence of the magnetic field. It can be anything. So that is the case when we have time-dependent magnetic field. Let us consider some other examples. In particular, motional electromotive force. For that case, we consider some uniform magnetic field in space and in time. This is constant. And we consider some straight conductor which is moving with velocity vector v along this magnetic field. The length of the conductor is L. So now we know, let's say this conductor is some metal. What is the feature of metals? They have mobile electrons, which are negatively charged carriers. So we have some negatively charged electrons inside this conductor. And now what happens with them as we move this conductor in external magnetic field? So there is magnetic field exerted on mobile charges in external magnetic force exerted on mobile charges, which are moving in external magnetic field. So that is the case. So in general, this straight conductor is electrically neutral because all mobile electrons negatively charged are compensated by positively charged ions in the crystalline lattice of this metal. However, because of magnetic field exerted on these electrons, since they move together with the conductor, we can consider that they are moving in external magnetic field. There will be some magnetic force pushing them to one of the edge of the conductor. So this will be FB, and as a result, we will build up some not compensated negative space charge at the edge of the straight conductor in the bottom edge. Since we had electrically neutral conductor at the beginning, and part of negative charge is kind of shifted towards the bottom part, what will be in the top part?
Positively charged ions.
Correctly, they are everywhere positively charged ions, but there will be uncompensated some space charge created by these positively charged ions, which charge will not be compensated by electrons because here we have some excessive amount of electrons, here we have less. So this uncompensated space charge created, let's say, positive space charge created by uncompensated positive ions in the crystal lattice of this metal. So now we create some electric field because we have two space charges, positive and negative. We create electric field. If we have electric field, what we have in exerted on these electrons? We obviously will have electric force. But why it doesn't work? Electric force. And this electric force will be in opposite direction to the magnetic force. So these rearrangements of space charges, negative and positive, will happen until which time? Moment of time. When both electric and magnetic force will compensate each other, so will be equal to each other, and in that case we will get some steady state condition, so which will be defined by the velocity of this conductor moving in the external magnetic field with given magnitude and orientation. So how we define the magnetic field, magnetic force? FB vector is equal to Q times velocity vector cross product magnetic field vector. Since they are perpendicular to each other, we can write that the magnitude of magnetic force is equal to Q times VB. Now we have expression for magnetic force. What is expression for electric force? Q times E vector. Or if we define it in terms of magnitude, Q times E. So now we are looking for the equilibrium condition, when we have steady state, Q times E is equal to Q V times B. Cancel out this Q, and eventually we get expression for electric field magnitude, which is induced in this straight conductor because of uniform motion with given velocity vector v in external magnetic field B, perpendicular to this velocity vector. Now, we would like to know what will be the potential difference, delta V, between the edges of the conductor. How do we address that? If we know magnitude of electric field induced in this conductor, how do we define potential difference between two? By length of the conductor. Yes. So we get E times L, and that will be equal to V times L times V. So that is the induced potential difference, or so-called motional electromotive force, which is induced in this conductor. So obviously, if we connect this mobile straight conductor to some conductive rails and connect them to a load resistor, there will be some current floating in this circuit. So we will form electric circuit. It will look like this. Say we have some resistor, we have conducting rails. Here we have this straight conductor and uniform magnetic field. So if this conductor is moving with some velocity vector, then obviously we create this motion electromotive force, which is induced electromotive force now in this electric circuit, straight conductor resistor, and that will cause some electric current running through this circuit. So let's say if we apply some force, F applied, to move this conductor, there will be change of position. So this, let's say here is axis X, here is the position coordinate X of the conductor, bless you. So while it's moving, the magnetic field flux B will be defined as BL times X. So that is the area which is covered here, and magnitude of magnetic field. If we want to determine the change, the rate of changing magnetic field flux, that will be BL times first derivative of x over time, which is velocity. So BLV. And electromotive force, which is induced, will be dFB over dt equals to minus BLV. So what will be electric current now in this circuit? If we neglect with the resistance of the rails conducting rails. So assume that the resistance is equal to 0 by load resistance. So in this case, induced current can be expressed as we can put here like magnitude of electromotive force divided by R, and that is B times L times V divided by resistance of this electric circuit. uh, so now let us summarize the discussion for today. We considered the Faraday's and Lenz's law, which are connected to each other and are always considered together. And specifically, we discussed this effect of induced electromotive force and induced electric current. Their orientation, like polarity and direction of the induced electromotive force and current, are defined by Lenz's law, which tells that they always oppose to the reasons which cause this induced electromotive force and current. And their magnitude is defined by Faraday's law, which tells us that it's equal to the rate of changing magnetic field flux through the current loop or wire loop, which we are considering. There are several options to change the magnetic field flux. It's time-dependent magnetic field, time-dependent um, area, and time-dependent orientation of the current loop with respect to the external magnetic field. So we also consider several applications of this induced electromotive force and current. However, there are different much more, and specifically one of the most important is the generating of electrical energy, because that's what's happening when we use electrical generators. We convert mechanical energy into uh, electrical. We are rotating the current loops in the generators in external magnetic field, so that converts mechanical energy into electrical. But we will discuss that a little bit later in more details. Now thank you very much for attention, and we will continue next time on Wednesday.